when you are in progressing in time, put a green or yellow post-it on your laptops. If you're behind or you have a question or you want help, put a red sticker and we will come and help you. Anyone in the room from UofT coders come and help you. So you don't need to be stay behind and get lost for the rest of the code. So please use us.
So for those of you who I gave Wi-Fi passwords to, I think you might have to add at utoronto.ca to the end. Leave them in. So try that.
So how it started. It was in statistics that it's been long that we are using learning. This machine learning, I think, have sort of hijacked a lot of concepts from statistics that has been long used. So I just wanted to pay a homage to statistics. So this learning problem has started long ago, and we have been doing it with, for example, fitting linear regression on our data and trying to train our model to be able to predict future inputs. So before, what we have been doing was, so we have a function that maps our x into the y space, and this is usually been done by a series of coefficients of x plus biases. And then we would define a mean squared error or any cost function, and we try to minimize our error. So the y hat minus y squared and the mean of it. Then people said, people started using. We wanted to be able to define nonlinear functions. So people started to do logistic regression for classic, or we wanted to do classification. So the image recognition came, or pattern recognition came along, and we wanted to do classification. So then logistic regression came, and it's a very nice model to do category, to classify your categories. But then for if you have multiple features and if you want to have nonlinear functions, then you need to add quadratic polynomials or a cube of your features, x1, x2, for example, x1 multiplied by x2, x1, x2, x3, and it will be really long and complicated. So people started at the same time, this idea of mimicking a neuron was born, and perceptron was built. That is a unit with a logistic activation function. So the same thing as logistic regression, but just the model representation was a bit different. So this time we had a unit that had a function, again mimicking a neuron that has dendrites that integrates its input and fires in a 0 or 1 manner, which would be a nonlinear function of those integrated inputs. They used logistic regression to mimic that. So this is exactly the integration of dendrites, the integration that is being done on dendrites, and logistic regression that is a 0 or 1 function would be your firing the spike or not firing the spike. So that's how perceptron was built or was born. And then they realized that when you put layers of these neurons, you can easily model any polynomial function or any nonlinear function of your input. And you're not constrained like in the original logistic regression. You're not constrained to define your features beforehand, or to define your polynomials beforehand. To define, do you want your x1 times x2 or x1 times x3, or you don't want them, or do you want x1 squared or x2 squared? How many of these polynomials do you need, or squared and cubes do you need? So with these layers, the neural network itself, through iterations, will learn the weights of each of these layers, and it will define your ultimate polynomial. So the basic idea is learning and minimizing your cost function. So the workflow is, you design your network, you design the weights, biases, if it's a fully connected layer, what is your activation function. These days, ReLU is very much used in a sort of logistic function, because it's a rectifier. It's simpler, and it's more efficient in functioning when you have a lot of layers. And then you define your cost function, what you want to be here. Then, well, I put here the how you will use in TensorFlow, just as an example. And then you train your model. You select your optimizer, because again, in for example, in linear regression, you had a cost function that you know is convex, and you knew it has one optimum minimum, and you could even do closed form analytic solution. You didn't need optimizer. But for more complex functions, more complex polynomials, you need to do, for example, a gradient descent. You need to train your model to use different weights, or different thetas. Sometimes people say theta instead of weight, to be able to reach to that minimum point. So you need the optimizer for that. And then you initialize your variables and train for how many steps that you defined. So this is the basic workflow for any learning problem that we will go ahead and do it in neural networks using TensorFlow. So what TensorFlow is, the name comes from tensor, that is any multidimensional array components with respect to basis. For example, any vector is an order one tensor, is an order one tensor. Any scalar is an order 0 tensor, and any matrix, for example, a color image that has 200 by 200 pixels and 3 channels, will be order 3 tensor. And because in neural networks, all these weight matrices are following, sort of, so that's why they call are flowing. They called it TensorFlow. So let's go ahead and do the code along. Any questions at this point? Okay. So I'll go. This will be posted. This notebook will be posted, but I'll code along with you. Let's start with importing TensorFlow. So import TensorFlow as TensorFlow. Then one thing that we can do is to define a constant, sorry. I'll call node 1 is pf.constant. Yeah, was it imported? You probably have installed it before, and importing is.
How do you get to that screen?
Oh, you should open your Jupyter notebook or Jupyter Lab, or this is in Python.
Okay.
So, yeah. Sorry, I jumped through. Yeah, sorry. I shouldn't have. So you either have a software for this, or you're using Jupyter Lab or Jupyter Notebook or PyCharm. So open a Python software or terminal or notebook.
Terminal.
Yeah, even terminal. And has anyone has everyone have installed TensorFlow? All of you have TensorFlow? Nice. So we want to define a constant. I want to define a constant. So in TensorFlow, we are building a graph at the beginning. At first, the first thing that you do in TensorFlow is to build the graph. And I want to build my graph using the first thing, make a constant. And then I want to make another constant, node 2. I want to put 4 in it. Let's see what it shows. If I print node 1 and node 2, it only gives me the descriptions of these two, because I'm just building the graph at this point. If you want to run your graph or run your model, you need to make a session first. So you do call it CSS, for example. CSS is TF session. That way, I'm creating a session for myself. Yeah, thank you. And now, if I run my session, node 1 and node 2, then I will see, okay, it's 3 and 4. So you build a graph of just 2 nodes, 2 constant nodes, and you run it. And of course, you didn't do any arithmetic on it or anything on it. So you can see them as 3 and 4 when you run your session. Now let's do something with them. Make another node, adding those two together. So tf.add. I put tf.add of node 1 and node 2 in node 3. And if I run the session,
excuse me, what is that? What's the section?
So what we do in TensorFlow is whatever you do in TensorFlow is to first build a graph, and then you make a session to run it, and that run is doing all the arithmetic or whatever arithmetic is doing, or whatever computations that is being done is done when you run your session. So this part that I did, whatever you're doing is just designing your graph or your network.
So for instance, when you say you added node 1 and node 2,
yes,
3 and 4, which means that you have 3 nodes here and 4 nodes?
No.
No, not yet.
One node that number 3 is on it, is in it. So that node 1 is a constant that is 3. That is number 3, value 3. Its value is 3. Then node 2, its value is 4. For now, it's just a constant. And then I'm adding node 1 and node 2. And if I run my session, again, if I don't run a session, nothing happens. If I run my session, so I do run session run node 3, then I will have, what do we expect to have? Yeah, we expect to have 7. Adding of node 1 and node 2 that were these two values, that were these two numbers. So I will have number 7.
So the comments, tell me if I understood correctly, the comments outside the session are the comments that you would write in an editor or anything. So
yeah.
It's just the code. But if you want to execute it,
exactly.
You will, start the session.
Yeah, correct.
Thank you.
You're welcome. So you don't need to, I didn't need to do this. I didn't need to make it in a node. You can also do any computation in the session itself, in the session run command itself, like this. So you can say Let me go higher. Session.run of node 1 plus node 3 plus, yeah, let's do node 3. Why not? So now I have 7 and I have 3 and I want to add them. So this was another way. This was one way to do it. And now I just want to, I don't want to store it in another node. I don't want to make another node. I just want to add these two. And so that's how I do it. I don't want to waste a node for it. So 3 and 7 will be 10. One other concept in TensorFlow is placeholder. So placeholder is like a variable that you design to then put any number or any value that you want. So this placeholder is used for your input. When you want to design your graph, the input layer, you call them all placeholder. I'll show you how. I'll show you why it's useful. So you call a placeholder. And for placeholder, you need to define its type. So I want it to be float 32. And I want to design B. See, I didn't put any value in it. I'm just saying that keep a place for me that its type is this type. And then I want B to be placeholder tf dot float 32. And then I want to add an adder node. Let's say I want to call this an adder node.
Sorry, what does placeholder mean? Is the context?
It's like a empty space that you assign or allocate to later put values in it. So this is used for your input layer. You want to give different training data into it. You don't want to design. It's not, for a variable, you immediately need to assign a number for it. For example, say A equals 5 or A equals something. But for placeholder, you don't need to. You just allocate a space or you allocate, memory for it to be later filled.
Okay.
So now then I want my adder node to be A plus B. Now I can keep this and then say, okay, let's pass a dictionary that assigns values 3 and 4.5 to it, for example. So now I do just in session run for adder node. I want to run the session for adder node when I'm assigning 3 to A and 4.5 to B. See, now I'm assigning. I didn't need to assign 3 or 4.5 to my A and B. I have these two, and I can now assign any number to them, or any tensor, any vector, any array. We will see more of this. So now we expect that our adder node to be 3 plus 4.5. Let's see what happens. Oh yes, 7.5. Now let's assign another value to our placeholders. Let's say session run for adder node A to be an array of 1 and 3, and B, I want my B to be 2 and 4.5. So we expect that we will have a pairwise sum of these two arrays. I have done something wrong. 1 parenthesis is too much. Sorry. Oh, 1 is, yeah. 1 is enough. So I have 3. That is 1 plus 2. And 7.5, that is 3 plus 4.5. So that's the idea behind placeholders. Now let's make a more please. Nothing. The same thing. They're doing the same thing. Please.
So I'm guessing that the placeholders are useful if you want to run a bunch of different functions and there are different values.
Exactly. Yeah. Thanks. So let's make a little bit more complicated graph. It's not just one adder. Let's say I want my A to be a constant. Number 4. You can name them, and I show you why. Because these you can then use for visualization of your graph. So I want to name this input A. TensorFlow has an add-on, TensorBoard, that will show you your graph. So these names are for that. And then I want my B to be another constant. Again, our 3, that its name is input B. Then C, I want to multiply these two together. So I do multiply, tf.multiply A and B, and name it multiply C. And then let's add more. Let's define D, that is the add of the sum of A and B again. And name it add D. Just to remember that D was add ourselves. And then E, I want it to be sum of my multiplication and my add. And I want to name it ID. Sorry. Then I put the session run E. When you do E, you run all of it in my output. Now, if you want to use TensorBoard to see your graph or to visualize your graph, you need to use a class that writes that graph to the disk to then use TensorBoard to see it. So, and that class is, let's call writer is tf.summary.filewriter. And you need to define the directory that you want it to be saved in. I call it my graphs test. I want it to be in an, in its own directory, not with other things. And then you have to add your sessions graph to this writer. So you add writer is, sorry, writer add graph. session.graph. The graph of your session is added to this writer. Hopefully it works. Let's run it. I put something wrong. Multiply. I'm a bit dizzy, so I may.
File writer.
Yeah, writer here. Thank you. Sorry, the pills are. Yeah. Add graph has this. Now, what we need to do is to go to your command line and call TensorBoard. TensorBoard comes with pip. So you already have it. You didn't need to install that. We go to wait. Let me write it here. So you need to type, well, no, let me. Yeah, I need to bring it. I need to bring my command line to your, here. So write this, TensorBoard. Yeah, I don't know how. Again. Yeah, this one I should go to edit, I guess, or no, to properties. So write TensorBoard. Now it's 2, sorry. Now it's too big. Yep. Here. Yeah. Oh, I didn't know. Yeah. So TensorBoard -- log directory and the directory that you gave it. When you type this, TensorBoard will open. And you will see your graph here. These are the two first things that we did. This is the last one. So we had input A, input B. We multiplied them, and also we added them together, and then we added the C and D, and we had the E. So no matter how complex your graph is, this will visualize it for you. But ours is really simple. This is the first example that we had, and these are the placeholder examples. But this is the last one. Yes?
Did you go back to the code? Just to get the last bit.
Yeah. Is anyone okay? Is everyone okay for now? What time is it? Let's do now. We're running out of time. Let's go fast to build the neural network. So what I wanted to show you is, so what we work today for our neural network is to classify handwritten digits, the famous MNIST database that is 60,000 examples of handwritten digits between 0 and 9. And we want to be able to, and each of them are stored in a 28 by 28 pixel image. And we have then 10,000 examples for testing. So we want to make a network. This is our 2-layer network. Our last layer is not shown here. Each pixel is in the 28 by 28 is one of our inputs. And we want to be able to classify these inputs to an array of zeros and ones that is one for our digits. So if it's, for example, the digit 0, we want last layer. In the last layer, we want our probabilities to be 1 and zeros for others. 1 for the first y and zeros for others. That's the way we code the digits instead of, because our program cannot output a digit. So it will assign probabilities to digits 0 to 1. This in the MNIST data in TensorFlow, we will use the MNIST data that is stored in TensorFlow, and it comes in flatted format. So this 28 by 28 pixel image is an array of 784 length. Let's import our data. I'll again code along. So what we need to do first is, where is my, sorry, I can't find my mouse to put it there. From future, we will need this import function. And from TensorFlow .examples .tutorials .mnist import input data. Hopefully I typed them correctly. And then put that input data read data sets. I want to put it in this directory. I mean, it's it's here in this directory, and I want to assign it as one hot true. So as I said, instead of having 0 to 1 digits, we will have an array of zeros and ones that is 1 for only 1 digit, and 10 long length of 10 array that is 1 for each digit. Again, I have a typo here. Thank you. Another typo. Let's see. Sorry, this is not import. This is print function. Why did I do that? Oh, thank you. Okay, it's running and it's downloading the data, hopefully. Yeah, perfect. Does everyone have the data? No? Maybe you're not. Mm-hmm. Since we don't have much time, I'll go fast. I don't know if. So first, let's do the let's assign our parameters. Okay. okay, as we said in our workflow. Our learning rate, I design it as 0.1. We need to have number of steps for our learning. I want to have 500. You need to define the batch size. Put as 128. And this display step is just to we want to display our accuracy in different steps in the learning phase, but with training phase, but we don't want for all the steps, so we want every 100 step. I want my first hidden layer to have 256 neurons or units. The number of hidden layer 2, I want it to have 256 again. My number of inputs is the 784 array that I said, 228 by 28. And my classes are 0 to 9, so we have 10 classes, either of the digits between 0 to 9. Then you define your inputs, placeholders for inputs. So X, you define it as placeholder that is a float. Yes?
Does the number of hidden layers, does that have to be a power of 2 or choose 6?
Yeah, it doesn't have to theoretically, but it's just nicer. We don't want to define the first size, but the array is anything by number of inputs, correct? And then our y, let's make this bigger, big X, capital X. And our y is assign placeholder for it, a float. And our output is the size of our number of classes. Let's run it. So before I have, if I have typos, I say it. Okay, no typos. Now let's make our weights and biases. So I call my weight. I define my weights as my H1 or my layer 1. Now we need variables because we need to define, we have values for them to put. We don't need to make placeholders for them. Choose from a normal distribution, random numbers from a normal distribution with the size of number of inputs. You know, this is our first tensor to the, and the size, and the other size is number of hidden layers, correct? So this is our first set of weights. And my H2 is TF variable set of numbers from chosen from a random and a normal distribution with the size of hidden layer number 1 by hidden layer number 2. And my output layer is a variable set, again, from random numbers from normal distribution with the size of hidden layer 2 and number of classes, correct? This is the output layer. Here. Now my biases. B1 is TF, Tensorflow variable, Tensorflow from random numbers from normal distribution. The size of hidden layer 1. Thank you. Oh yeah. B1 and then B2. TF. And all the variables had to be, sorry. So this one has the size of hidden layer 2. And I have a mistake. And my output bias is the size of hopefully I haven't. Thank you. Now let's create our model. Define my neural net of X as my layer 1 will be so the sum of, remember it was W times X, the two matrices times together. So we write it like this: this matrix multiplication function is MAT-MUL, matmul of X, and weights of H1 and biases B1, biases B1.
B1?
Sorry. So this is the X times our weights plus then this add is plus adding this term to the biases or biases to that term. So we have our WX plus B here in layer 2, the same thing. We need to add to sum or add the biases to our matrix multiplication of now layer 1. Because the input to this is layer 1. Layer 1 and then weights of H2. Matrix multiplication added to the biases, or biases added to the matrix multiplication. And finally, our output layer. Matrix multiplication of layer 2 and the weights of out. See here, we can also write just plus biases. We could have written cross biases for the previous ones too, just to show you that we can have different ways of writing it. And we close the function. Hopefully it will run without. Again, I have a lot here. Now, we need to construct our optimizer and stuff. So our model, our logits are neural net of X. Now we want to say this is my model, my loss is my neural network. Now my loss is, I'll tell you what it's mean of. So the mean of softmax cross entropy. Because we assume that these digits are, the probability of them, or the classes are mutually exclusive. So we want the cross entropy of them later to be 0. And this softmax is giving this probability that we later want to minimize. Don't know why I did that. And labels are Y. The labels are Y. We need to design our select our optimizer. So my optimizer is, let's choose Adam. That is stochastic gradient descent. With learning rate of our learning rate. And this is saying that, hey, I want it to be minimized. What do we want to minimize? This, our loss function. So we want to minimize the entropy between the classes to have the maximum accuracy or the least error.
Learning rate was that for every iteration, how much you change the...
Yes, the weights. Now, evaluate model. To evaluate model, we say, okay, my correct cred is TF equal, if it is, tell me if the max of logits and max of logits or 1 and max of y1. Sorry. And then the accuracy will be the mean of this reduce here is just in TensorFlow, they say, reduce my tensor to its mean. That's why it's called reduce mean. It's not reducing anything. It's just the way they called this mean function. Instead of calling it mean, they called it reduce my tensor to its mean. It's funny. But don't mistake it for minimizing or training or anything. So we want to have our average of our errors, or reverse our accuracy. And then we need to initialize, of course. This is an initializer function defined in TensorFlow. Hopefully I don't have any typos. Of course I have. Let's find it. What does it say? Variable initializer. What is wrong? Variables. Global variables initializer. Okay. Oof, we're almost done. We just need to run our session. And that's it. Let's run and get done with this. Now, I want for my session to run as sesh. And I want to run first initialize, run the initializer, run init for me first. Then just to say when to display. Oh, sorry, this is for now. This is defining the loop for training. Steps, number of steps. Go to run for me. Let me bring it up. Fetch the X batch and the Y batch from mnist. We know our batch size. Again, another typo. And I want to run my session for training. Dictionary B. So I assigned X, my batch to X and my Y batch to Y. Remember we had placeholder for them? This part is just for saying, just show every 10 step. Every 100 steps, sorry. Display step. If it's step, now compute loss and see as session run of my loss function and accuracy and feedback again batch and Y batch to Y. In each step, print me what step are you in. Print me my loss. Just 4 decimals for loss. I don't need more. For training accuracy. Just need 3 decimals. Okay, just to show that this is when and then at the end we want to test it as well on a test set. So just quickly, let's also run it on a test and show what was it. I get from the, I put X as, again, now we want to feed another thing to our placeholder, another set of data. This time is our test data. So just a few test images.
It should be on 4.
In the for loop. I think it's in the for loop.
So for every iteration, you are going to test it.
Mm-hmm. This one, yes. This one is the end. So it's out. Oops. Yeah, sorry. It should also be out of for loop. So where's y? Wait. And also our y. That is our labels. Again, if I don't have any hopefully I won't have a typo and it will run.
That's up there, and the third line from the 4 statement.
Mm-hmm. Thank you. That's good. Okay, it's running every 100 step. And it's finished, so we can see that our loss is getting smaller and our accuracy is getting higher. And our last one, the test accuracy was 0.8. So it's pretty fast. TensorFlow is really nice, and the package, everything is packaged for you. If it was in other languages, you had to, at least in MATLAB, you have to write a lot of these yourself. But with just a few lines of code, you have a neural network. That was my part. unfortunately, we don't have time for. We already passed the time. I'm really sorry. I was slow. We wanted to also show the same thing being done in Keras. Keras, thanks. Maybe we will have another session next terms on more advanced, maybe convolutional neural networks with Keras or something like that. Sorry, I took too much time.